Welcome everyone. I'm Jonathan Ferguson, and I teach game design here at Champlain College. And I'm working to host operations at the podium here in the room. So you can't see me, but I'm going to do the introduction for Michael Ferguson, who is our presenter today. Michael is a principal software engineer at HPE or Hewlett Packard Enterprise. He's been working in open source projects for quite a long time, in fact. So this latest project that he's involved in is called Chapel, and he's going to present about the Chapel language, which is very exciting. I don't know if any of you guys got to see the blog post, but the blog post was extremely compelling if you are used to speed comparisons in C, C++, or Rust. Seeing performance improvement of 10x is something to take notice of, I think. So I think that's all I need to say, but I really appreciate Michael for doing this remote presentation for us. So you're on.
All right, thanks very much. I'd like to also note I have 3 of my colleagues from my team who are hanging out on the Zoom. So, you know, they'll if I get stuck, right, they can help. Anyway, I will just get going. So this is sort of an outline for what I have in mind for today. So I'm not going to go through all of the outline. You can look at it, obviously. But the key thing is that I'm going to talk at you for around 20 minutes. And then we'll do some Q&A and live demo time. And then I just have a couple of slides to do for a wrap up. So that's my plan. So I'm going to start out with this motivational piece about sorting in standard libraries. And this is what that blog post that Jonathan referred to is about. So let's get going on that. So why would we be thinking about this? Well, most standard libraries include a sort routine, and sorting is pretty much an essential building block. Supports things like group by, if you're familiar with data analysis tools. There's Arcuda is one that we'll talk about more, but group by is in pandas too. Supports indexing, searching, lots of other algorithms. So sorting is pretty helpful for a lot of uses. So let's just say, what do we see if we investigate the performance of standard library sort routines? You know, you take your language, kind of install it, and then just run some sort. What happens? And then why am I focusing on standard libraries? Of course, there are all kinds of sort implementations out in the world, but here I'm going to focus only on standard libraries. And the reason is that they're more likely to be used in practice than anything else. They, to some degree, show what a programming language has to offer, because oftentimes the people who made the sort in the standard library might have been making the programming language too. They set an example for other libraries in the language, and then they form a kind of a common language or vocabulary for programmers in the language, right? Because it's a standard library, everybody will know about how to use it, or at least might be expected to. Okay, so what's the benchmark? The benchmark is take 1 GB byte of memory, that is how much would fit in 1 GB of RAM stick, right? Of 64-bit integers. So this turns out to be this number, 128 times 1024 times 1024 integers. That's the amount of integers we're going to sort. And we're going to fill the integers with we're going to initialize them all with random values, and then we're just going to sort it and see what happens. Okay, and we're going to do it on this system right here, which is just my PC. It's got 16 cores, 64 gigabytes of memory. I've got the motherboard there in case you wanted to reproduce my results. And it's running a recent version of Ubuntu. And there pictured, I've got my Powell programming consultant who helps with all such matters. So note that this system is only around $1,500. This is not that expensive a computer. Sure, you can buy a $300 computer, but this is not like one that has a $10,000 CPU or anything, right? All right, let's see what we get. So here is the benchmark that I used to see how fast Python's standard library sort goes. So, you know, on the top, there's some preliminary materials. And by the way, do you see my cursor?
Yes.
Yes.
Okay, excellent. On the top, there's some preliminary materials, and then we say, well, here's that n that I picked that's gonna make as many 64-bit numbers as would fit in a gigabyte of memory. And then we make an array. This just fills it in. This big long line of Fs is just setting it so that they go up to 64 bits, and it fills it in with random values. We start timing, we do the sort, and then we print out the speed. Easy peasy. Okay. So then what's this look like in Chapel? Well, it's pretty similar. We're using some different libraries because it's a different language. We've set our problem size, create our array that goes up to that size, fill it in with random values, start timing, run the standard library sort, and then print out the timing, right? So you can see these two programs are both pretty simple. In fact, they've got, I would say, pretty equivalent complexity, right? They've got these same sort of regions. Obviously, the languages are different, and obviously, you might have no idea what any of these symbols mean in here. But the point is that in terms of like, are these complicated programs? They're both really pretty simple. They're just using the standard library to call sort on some array, right? All right. But what happens when you compare their performance? This is what happens. So here's the Chapel sort speed at something like 540 million integers per second. And then Python's over here at, I believe, 2. Um, and then in between, we've got lots of other interesting languages. But compared to the closest one in this particular measurement was Rust, and Chapel was 10 times faster than Rust. C oddly enough, was faster than C++, but Chapel is still faster than that by 15 times. And then we're about 200 times faster than Python sort. So, okay, that's fine. You might say, well, that's cool that now we know about this performance information on your PC, but I wasn't actually going to do any computing on your PC. I've got some kind of server in a server room somewhere, and that's where I'm going to actually do my computing. So what's this going to look like there? Well, actually, it's even more extreme. So here's a one-socket server, AMD EPYC server with 32 cores. And now Chapel is 25 times faster than QSort in C. On the earlier slide, it was 15, and now it's 400 times faster than Python. Okay, if we go to a two-socket server with AMD EPYC 64 with 64 cores, because it's two sockets, then it's almost double that, right? So now we're 1,000 times faster than Python. Okay, that's cool. So why? Why is it so different in performance? Well, there's one big reason, which is that these are all parallel systems. They're multi-core, right? And Chapel used all the cores, and all the things I'm comparing with used one core. So you could say, well, that's not a fair comparison, but that's the point, right? If you want to do parallel programming and you want to make your programs go fast, you want it to be easy, right? And the parallel programming language can make it easy to use the parallel hardware. And then in addition, if the parallel language has a parallel standard library, like what we were using when we called sort, that brings additional productivity. And both of these things are something that Chapel offers. All right, so now I'm going to go into what is Chapel. Tell you a little bit more about that. So the sorting case is sort of our motivation in a way. So Chapel's a modern parallel programming language. It's portable, scalable, open source, being created in a collaborative manner with the goal of supporting general parallel programming and to make parallel programming at scale far more productive. So at scale might mean like on a cluster or a supercomputer. So if we want to define what is productive parallel programming, a potential definition was you might think of a parallel programming language that was as programmable or as easy as Python, but it's as fast as Fortran or C or C++, as scalable as MPI or SHMEM, which don't worry if you don't know what these things are, as GPU ready as these technologies like CUDA, OpenMP, OpenCL, and as portable as C. And I hope I've already shown you with the sort example that we do have something that's approximately as programmable as Python, at least if you're doing that sort benchmark. So Chapel programs are compact and they're clear and they're competitive. So here I'm showing two different benchmarks written with competing technologies. These are all technologies for distributed memory programming. And then in the same, we can solve the same, we can write the same benchmarks in Chapel with a lot less work and a lot less code. And these are still distributed memory benchmarks. And then they perform about as well in the top box as the other benchmark in the background. On the bottom, actually, a whole lot better than the the sort of more traditional tool. All right. So I've just teased a little bit about how does Chapel compare to other languages because we talked about it with sort, and I just talked about it a little bit with distributed memory parallel programming, although I didn't go into much detail there. We actually have more information about how Chapel compares to other languages because we participate in something called the Computer Programming Languages Benchmarks Game. And there's a little tiny URL at the bottom of the screen that it's a website where people make um, implementations of different benchmarks in different languages, and then people time the different benchmarks and see how complex they are. So in this picture, we've got a square for the simplest benchmark in a particular language and a circle for the fastest one, right? And this picture actually averages all of it's sort of considering all of the different benchmark problems. So what you want in this picture is you want to have fast execution time, so that means down on the y-axis, and you want it to be small, as in a simple program, so then it's left on the x-axis. So you want to be in this corner down here. So I'm going to zoom in on this picture a little bit, and you can see that Chapel's pretty much occupying this corner of relatively small while being relatively fast. So that's cool. Actually, I have one more piece of information of comparing Chapel with other programming languages in terms of productivity. This is from an academic publication where they were evaluating Chapel, Python plus Numba, and Julia for an optimization problem. They did their experiments on a single machine, a dual socket 32 core machine, and they found that Chapel was more productive in terms of offering performance for a certain amount of code. All right, well, if it's so productive and everything, what do people who are using it have to say about it? Well, here's a quote from Nelson, Dr. Nelson Luis Diaz, who has been using Chapel for about 2 years. He works with turbulence data sets and models for hydrology. And he says he'd like to see Chapel become a programming language for everybody. He says it's fast, parallelization is really easy, and I didn't know I could get so much from my desktop until I used it. And then this is actually from a talk, and I think we'll try to make these slides available somehow so you can follow these various links if you're interested. A second user we have a quote from here is Professor Eric Laurendeau, who's from Polytechnique Montreal and is a professor of mechanical engineering. His group has been creating a computational fluid dynamics package with Chapel. It's called CHAMPS that I'll say a little more about later. It's proved to be much more productive than their previous technology that was using C and Python. And so he says about that Chapel promotes programming efficiency. They ask students at the master's degree level to do stuff that would take 2 years, and they do it in 3 months. All right, cool, cool. So what about applications of Chapel? Are people doing real work with it? They sure are. So here's a bunch of applications of Chapel that we know about, and I'll go into some of these briefly. So the first is this CHAMPS project that I just touched on with the quote from Professor Laurendeau. CHAMPS is a 3D computational fluid dynamics framework for airplane simulation. It's written in 85,000 lines or so of chapel code over 3 years. It's written by Professor Eric Laurendeau's students and postdocs at Polytechnique Montreal, and they use Chapel to do this because they found it to have good performance and scalability, while the students found it far more productive than what other technologies they had, and it enabled them to compete with their fluid dynamics package in terms of making simulation results with more established computational fluid dynamics groups. Let's look at another application. This one's called CHOP. CHOP is a optimization package. It's doing lots of tree-based branch and bound operations made by some of our European friends, Tiago and Noradine. It's open source, and the reason that they're using Chapel is that they found it to be more productive than alternative technologies. And some of the people involved in this were making that paper I referred to earlier on optimization. Okay, and then let's look at one more application in Chapel, which is Arcuda. So if you have any background in programming with Python, you might find this one interesting. Arcuda is a project that's thinking about doing data science in Python at a big scale. So if you imagine you've got really big data science really big data science problems to solve, and the people who you have to do the data science are Python programmers, and you have access to high performance computing systems, how can you use your Python programmers to even solve your data science problems? So Arcuda is a Python framework to do interactive high performance computing. There's an Arcuda client that's written in Python. The user, the data scientist, will use that and write code that's familiar to them because it's similar to NumPy and Pandas. And behind the scenes, the Arcuda client communicates with an Arcuda server that's written in Chapel and runs on a supercomputer or cluster. This allows for really big exploration of data, exploration of really large data. So as it says here, you can compute massive scale results like array over arrays the size of that are a number of terabytes within a few seconds to minutes. So you can actually be thinking about a problem, do an experiment, and then continue thinking without having to have your thought loop be stopped. And then this project's, 30,000 lines or so of Chapel and 25,000 lines of Python, and it's been in development since 2019. And it's open source also, so you can go and explore that project. It's written by it was originally authored by Mike Merrill and Bill Roos from the Department of Defense, and they chose Chapel to make Arcuda because they found it to be close to Python in terms of being easy to use. It allowed them to make Arcuda quickly, and then people who are familiar with Python who look under the hood at what's all this Chapel code seem to be able to work with it reasonably well. And then furthermore, they got the performance and scalability they needed, and then lastly, it was important to them that they were able to do a lot of the development on a laptop and then run the same computations on a supercomputer at a larger scale. All right, so those have been some of the applications, just to tease them. A lot of these have been presented at our annual workshop called Chapel Implementers and Users Workshop. So if you get the slides here, you can follow those links to see the authors of these pieces talk about their projects themselves. All right. So that is where I'm ready to stop and go into doing demos. If there's, oh yeah, demos and Q&A. So I want the next section of the talk to be any kind of question and answers that, asking and answering any questions that you have. And I have a bunch of live demos to show you that go into a bunch of different features of Chapel. So now's a great time for me to pause and get some water and for you to think about if you have a question.
Like live, you guys can just raise your hand or whatever. I'll call on you. All right, we have a question from the chat, Michael. Is Chapel statically typed from DJ?
Yes, it is a you and we'll see this in some of the demos, but it is a compile ahead of time kind of language like C or C++ or Fortran or Rust or many other languages, right? Um, it does have pretty good support for generic programming, and if you squint a little bit, if you're used to like Python, duck typing, the generic code actually is pretty similar.
Do you have a sense for the size of the community? Like, will it show up in the developer survey, like within a couple of years?
I don't know what will happen in a couple years. We are a relatively small but growing community right now. I think one of the things that is challenging for this project is that it is pretty ambitious to try to make a general tool for parallel programming. And people who want to do parallel programming usually care deeply about performance, and that means that the tool has to reach a certain level of performance before they'll consider it. I think we're pretty much there for at least for a lot of things with Chapel, but this kind of thing takes a while.
Thanks.
We have another question from BJ. Do you see applications for Chapel in the AI space for AI model development, training, and inference?
I think that's an interesting question. I know that AI is a hot topic. I don't personally know a lot about how all of those things are built, so it's hard for me to have a lot of opinion on that. We have done some explorations of training some simple models in Chapel. And then the next question is, how does Chapel support GPUs? And that's one of the things I would like to demo. So maybe I will do a little bit of demoing and then we can answer more questions after that.
Cool.
Let's see here. All right. Let me get to my first window. Okay, so the first demo is, say I wanted to get, I thought I deleted that. Always just, say I wanted to get Chapel, what would I do? Want to just get going, try it out. So you can go to our website. Our website has a download button. So this will let you download a release. Depending on what you're doing, like if you wanted to reproduce my sort results, you would need to use our GitHub repository. But either way, it's pretty similar what you would do. So I'm going to clone the GitHub repository, which is also linked from here in the little nice Octocat picture. Right, so here's our GitHub page. Anyway, I'm going to clone that. It's not that different if you download a release. You would just download the tarball and then uncompress it. All right, so we've got our checkout. So in here, this is our Chapel tree. I just go into here. So the next thing you do if you were trying to use this on a system is you'd need to know, do I have the prerequisites installed? So this page has the prerequisites. Let me show you how you would get to this page because you won't just be able to paste a link like I just did. So if you go to the documentation page, you can go to quick start instructions. This has instructions on how to get going from the latest release in the simplest configuration, you can go to the prerequisites page where we have for a whole lot of different OSs the commands to install the dependencies. I already have the dependencies installed on my system, so there's nothing to do there. So the next thing I'm going to do is I'm going to run this script. This thing, the main point of it is that it adjusts the path so that I can run the Chapel compiler. The next thing is that Chapel has lots of configuration uh, options for doing things like targeting a GPU or a supercomputer or just your local machine. And this is our tool for printing out what the current configuration is. I want to highlight this one here is saying there's no communication layer. That means I'm going to be building for a local machine. So in fact, I'm running and building on this guy here. So I'll just launch a build here on that, and that will complete in a second, not a second, but in a minute. And then we'll from there we'll go and we'll build a Hello World program. Any questions while we're doing our build?
Yeah, Diana.
Why aren't there more languages that take advantages of multiple cores?
Did you?
Oh, that's an interesting question.
This helpful. Why is it not more common?
I think that part of it is that a lot of people see that as the role of libraries. But it is certainly the case that some of the newer languages have more built-in support for parallel computing, right? As compared to something like C, where it was kind of retrofitted to even have basic support for threads. If I did the quick start build, it would have been quicker. That turns off a lot of the dependencies that it's building now. But we like our default configuration for performance. Okay, so now I've got it built, and now the name of our compiler is Chapel CHPL. By the way, that stands for Cascade High Productivity Language. So this is in my path because of that script I ran earlier. Of course, you could put it in your path some other way. So I'm going to use it to compile a Hello World program. So this is just a tiny Hello World program. It just prints out Hello World. So let's just compile that and see what happens. So when you compile something, it looks at the file name and then puts the output in the same thing. You could put that in a different file with -o. And then you'll notice it pauses for a second when we compile Hello World. We know that in comparison to something like a C compiler, our compiler is relatively slow. And that is one of the things we're working on. The reason that it's slow is that it's a whole program compiler. So that means it compiles the entire standard library in addition to the little program Hello World. So that's what I wanted to do for the installation part. Next, I was going to show you a little bit about some Chapel language ideas, on and co for all. And then after that, I was going to talk about GPUs. Any questions? Should we go on to on and co for all?
We're good to go.
All right. So just for fun, to do the on and co for all part, I'm going to log into a supercomputer. So this supercomputer is called Horizon. And I forgot to paste all of this stuff before I started. So just bear with me for a second. So I'm going into, I have a checkout ahead of time. I'm just doing the build again, just to make sure everything's up to date. I did that same kind of source thing, right? So now I can do which chapel, and you can see it's here. Okay, so let's first compile hello world, because if hello world doesn't work, then you have a problem. And this hello world just has a write line in it, right? Which is kind of like, printf or something like that. So if I just run it, it says you have to tell me how many locales you want to run on. And in chat, locale is sort of a chapel term for a machine or a node. This program is just printing out hello world, so it makes sense to just run it on one node. Okay, well, that was fun. What if I do, sorry, I'll make a new program called hello2. Oh, so in this one, I'm going to just, oh boy, I'm going to, you know what, I can't talk and type at the same time, fatal error. I'm gonna show you about the on statement in this program. So I've got a first hello world output, and it's print using a built-in thing called here that's like what locale you're running on. And then I've got this on statement that says go run somewhere else, but it doesn't introduce any parallelism. This is still a sequential program. So it's going to do this, then it's going to go on to locale number 1, and then it's going to do that. And it's going to print out the name of each locale. So let's compile that. And then we'll run it once it's done compiling. And I'm just going to pretend that I don't know any better, and I'm going to accidentally run it with the wrong number of locales. So I got an array index out of bounds. So this thing is an array access to the built-in locales array, and I went to access number 1, but it's only got 0 in it when I run on one locale. So that's what that looks like. That's bounds checking that's on with regular compiles, but if you use -- fast, it turns it off for performance. Anyway, so I'm just going to cat the program so you can see it at the same time, right? We ran here on the starting locale, always starts on locale 0, and we said on locales 1, and it went over to a different host. Okay, that's cool, but what if I wanted to write a parallel program? Let's look at a parallel but local program. So this one I'm using cofrall. Cofrall is a loop form that creates a task for every iteration. So then I'm just printing out something for all of the 10 tasks. Okay, that's cool. Let's just do it and see what happens. Let me get it so that it's on the same screen, and then we'll run it. So I can run this on one locale, and it printed out hello from these different tasks. You'll notice they came out in a different order because they're tasks they're running in parallel. And they're all running on locale 0 because I haven't said on somewhere else. If I run it with 2 locales, they're still running on locale 0 because I haven't said go do something somewhere else. Okay, well, what if I actually wanted to run on all the locales in my system all at once? Well, the locales array, we can use cofrall to iterate over the locales array to create a task for every locale. And then we can use on locale to go and run something on there in that task, and then we can print something out. So now we'll run something in parallel across all the locales. Let me just get that shown there, and then I will compile it, and then we can see what happens when we run that. I'll run on 3 locales just for fun. So this one will run those tasks all at the same time on the different machines. So who knows what order it's going to come out in because these are all running in parallel. All right. I want to show you one more thing while I'm here at the supercomputer. This is the program that I showed on the slide earlier that was called Stream. And what this does is it creates block distributed arrays across a bunch of as many machines as you're running on. And so this says make a block distribution from 1 to n, and then this makes three arrays over that same block distribution from 1 to n. It sets up B and C to be 2 and 1, and then it computes this thing. These things are whole array operations. So this sets all of the elements of B to be the number 2. B is an array of real numbers, but we're setting all of them to be 2 at the same time, and this will run in parallel. Similarly, this thing is a whole array operation. It sets each corresponding element of A to the corresponding element of B plus alpha times the corresponding element of C. So this thing is called a promoted expression, and in Chapel it's equivalent to a for all loop. So I haven't shown you for all loops, but there are data parallel idiom for saying I've got lots of stuff to do, do it in parallel. Okay. So that's what I've got there for showing you some of the Chapel ideas. The next thing I'm going to do is show you some programs running on GPUs. Any questions?
Are you gonna run that?
There's
Yeah.
one question there.
Yeah, I see the question.
You want me to run it?
Yeah.
Okay. All right. Well, since this thing does the same thing as the other one, I will, I'm not like actually using the result at all. Oh yeah, that's true. We rename something. That's how it goes with slides, you know. Okay, so data par. So we'll run it on 2 locales. So it's gonna make 1,000,000 elements, and I didn't print out anything about the result, so we didn't time it or anything, but I did run it.
Okay, so there was a question or two from BJ. He's curious about interleaving and locking problems. So is it possible to manually set locks, or is that not even necessary?
Yes, locking is important depending on what you're doing. Oftentimes in distributed memory programming, especially if you have another way to do it that's not locking, it might go better. But we do have some lock kind of features available in the library, and there's also a language type called a sync variable that's sort of kind of a, if you squint a little bit, it's kind of like a locked value or something. But that's sort of, I'm not going to have time to kind of go into those. But those things exist as features.
Very cool. Any other questions? Great, proceed. Thanks.
Okay. Let's go do something on a GPU. All right. We'll go over to this NVIDIA GPU system. And on both, I'm going to show the same program running on an AMD GPU system and a NVIDIA GPU system, and it is this program. This program is it's called Jacobi. It's a simplified form of a stencil operation that's commonly found in physical simulations or image processing. So this program is going to do a bunch of steps. It's got some array size. Just for doing a demo, my array size is really small. Here it says, so we've written this function to say Jacobi and it accepts an argument. This is actually one of those generic arguments I was talking about that feel a little bit like Python code. So this thing, we're passing in either a GPU or just the regular CPU. And then it says an on statement to say, go run it on the CPU or go run it on the GPU. And then I've got these things to print out if we're doing kernel launches. And then here, these for all loops are going to run on the GPU. Okay. So I would like to have that program sort of sit. I'm not sure if there's going to be room to have the program sitting here and also run it because, you know, my windows are too big, but so let's see. Here I am on the NVIDIA system. So I will compile it and I'll call the output Jacobi NVIDIA, and then we'll run that and see what happens.
What does fast do?
that turns on optimization and it turns off the bounds checking.
Okay.
If you're doing anything where you need it to go fast, you should use fast. So we see this, I have sort of activated a bunch of, in here I activated this verbose GPU thing, and that got it to print out when it was doing a kernel launch on the GPU for these different elements, right? So like line 21, what's line 21? So we got a kernel launch right here. Since this is running a bunch of steps, actually, it does a bunch of kernel launches for those in a repeated way, right? And then we got our sort of answer here, and we ran it on the CPU, and we got that answer, and looks like they line up, so life is good. Let's just do the same thing on the NVIDIA system. Wait, that was the NVIDIA system. Let's do the same thing on the AMD system. So this one over here is the AMD system, and I'm going to just compile it again. I'm just going to call it Jacobi AMD, because actually I'm using my shared home directory that's the same on both of them. So, and then we'll run that and you'll see a pretty similar situation. So we've got the same kind of thing with the kernel launches, got the same output. So we can do GPU programming that's portable between NVIDIA and AMD GPUs. Our GPU effort is rapidly improving, but it is far enough along that at least simple things work pretty well. So that's the GPU part. The next thing I have in mind is to show you our CUDA. Any questions about the GPU part? And am I at -1 minutes?
Oh, no, you're fine. You can keep going.
All right.
So we have another question from BJ. He wants to know if you can divide large workloads across multiple GPUs or distributed computation.
Yes, we already have the ability to use those on statements that I showed you to run run something on multiple GPUs within a node. And we're making rapid progress toward having the ability to do something like create a block distributed array that's distributed across GPU memories on many nodes in a cluster or supercomputer. And my colleague Daniel, who posted in the chat, has also been working some on the GPU stuff and posted a good link to a starting point for learning more about GPU programming in Chapel.
Right. Any more questions here?
Can you show us again in the code the part that says do this on the GPU?
Yes. So it's actually right here. So this, because it got past a variable, this is actually, you know, on here.gpus at 0, right? And GPUs is an array, so I could say something like co for all GPU in here.gpus, right? Like if I wanted to do something on all the GPUs. Right, and then I could do something like that. Right, so this kind of pattern is similar to what we were doing to run something across all of the nodes in our distributed job. And this is, I think, one of the really interesting things to me is that for some of the hard programming problems we face within a node, actually the distributed memory techniques make sense, right? So our idea of running in a place on a locale makes sense for GPUs just as well as it does for different nodes in a cluster or supercomputer.
Thanks.
Great. Any other questions?
Let's do something with our CUDA. It'll be fun. All right. All right, let's see here. So first I've got my Arcuda set up here. Let me see. This one's got a couple more steps to it. So, okay, so I'm going to go on the supercomputer and I'm going to start an Arcuda server that I have compiled ahead of time. And then I'm going to make a note of that piece. And I'm going to set it, I have to create an SSH tunnel to get this to work. So let me do that really quick. Okay, so now I've got my Arcuda server, and if things are working correctly, I should be able to SSH to it. So now, just for fun, I will launch a Jupyter notebook, because I don't know, I think everyone loves Jupyter notebooks, right? I'll make a new one instead of playing with the ones that I was. So I can import Arcuda. I've already got this set up so that it knows what Arcuda is. And then I can connect. This is connecting to localhost because I've got an SSH tunnel. So when I connect it, actually, we can see that the Arcuda server printed out some stuff. It's, you know, kind of a mess, but something happened. So with Arcuda, the idea here is that I can write code like in Python. And one of the things in my presentation I showed you was how to sort about 1 GB of memory in Python, right? So I can do that same thing here in Arcuda. So I created my 1 GB of integers, and then I asked Arcuda to sort it. I can print out part of the array that I sorted. Hopefully that's in sorted order. Another thing Arcuda supports is data frames. So if you're doing exploratory data analysis, you might want to make some data frames. I'm just gonna, oops, I meant to put more in there. Let's just try that here. So this thing is just setting up a data frame so that we have something to play with. So it's kind of like a little table shown there. I can run group by and sort it by last name. I've got two different people named Doe, one Smith and one Brown. So I can group it and then I can count it. And then we'll see that we have two people named Doe. Right? So Arcuda is cool. I did that with, 4 things, but the use case for Arcuda is, maybe you have 1 billion, right? And then you can still do that in a few seconds to a minute or something like that. So that's what I have to show you about Arcuda. Any questions about that?
Yeah, quick question. Can you do kind of data science, linear algebra operations like SVDs and things like that with Arcuda?
I don't know. That's not one that I know the answer to. Um, I we could pull up the Arcuda documentation, but that's just not one that I know the answer to. I think it's definitely something that Arcuda is capable of doing if someone added it.
Mhm.
But I do not know if it is already present.
Okay.
Well, any other questions in here? All right, great.
All right. Well, I had in my presentation, I have to let me tell it that I want to exit nicely. I had just like 2 more slides to show as sort of a wrap up. So let me do that. And let's see. All right. So Chapel's primarily developed by this group of people who work at HPE, and I am among them. It's unique among programming languages because it has these features for scalable computing. It supports pretty clean and concise code related to other approaches for parallel computing. It's useful from laptops to supercomputers or desktop machines like my guy here. It's already in use for productive parallel computing at scale. Our users are benefiting from the productivity and performance of it. It's scaling to thousands of nodes, millions of cores, but also works great on small scale. Our GPU support is maturing rapidly. Something we've wanted to have for a long time was to support any parallel algorithm on any parallel hardware as a goal. And I think the GPU support are going a long way towards demonstrating that we have that kind of portability. And we're interested in helping new users and fostering new collaborations. So if you're interested in talking with us more, we'll find a way to make these slides available so you don't have to try to copy all of these down. But there's lots of ways to reach out. And with that, we can have any last questions.
Is it callable by the languages? Like, did I call it from C or something else, like embedded in a program?
Yes. Actually, Chapel has a pretty extensive support for calling C from Chapel. We also have the ability to create a library that is your Chapel program and call that from Fortran, Python, or C, where I think it depends on what you're doing, kind of how well that goes with what we've built so far. But those capabilities exist.
What have been some of the benefits and downsides of building Chapel in the open, like as an open source project from the beginning?
Uh, that's an interesting question. My own reaction to my own opinion is that the main benefit is that I I think people will have a really hard time adopting a programming language that at least does not have an open source implementation available. Because I think it's easier to see longevity in an open source project than it is a proprietary software done by a company. I think that so that's like what I would see as a big benefit. I think a challenge is um, we don't all what let me try. A challenge is occasionally we will find people who want to argue with us. So that can happen in any open source project, right? If you're doing all of your work out in the open, then there may well be people who just want to disagree with you. Was that enough of an answer for your question?
Maybe another organizational question. The development of the core language, is it all within HPE, or do you also have like external collaborator on the core? And how do you make that work?
So I think actually we have pretty good processes right now to support external collaborators, but right now it's happening all within HPE. When I started working with Chapel, actually I was an external collaborator, and then I went in and joined the team at Cray and then HPE. And I was able to do some relatively large changes while I was an external collaborator. I created the I/O system that we use today. I changed the way that all of the arrays represented memory. And I'm sure a bunch of other stuff. Oh yeah, I also added LLVM support to the compiler, right? So it's possible. Just depends on what people are motivated and interested to do.
We have another question from Jay. What is HP's business interest in supporting Chapel's development?
Yeah, that's an interesting question. So the way that I see it is that HPE would like to sell big parallel computers, but there's lots of people who maybe don't know that they want or need a big parallel computer because they might not know how to program a big computer. So if we have something that is more accessible to people, then that might increase the market, right? If that made sense.
Questions? So I think that's pretty much it. Thank you very much, Michael. I really appreciate your presentation.